Two reactions are given, which both a combination of solids and gas components in the reaction scheme, and they are going to reach equilibrium at 900 Kelvin. Enough information is given to calculate the equilibrium constant for each of these two reactions at 900 Kelvin. We can now write our equilibrium composition equation for each of the reactions in terms of the mole fractions of the gaseous components and the pressure in our reactor. We are asked to calculate the pressure in the reactor such that the equilibrium mole fraction of gas E is 10%. In addition to the pressure, we have two more unknowns, the mole fraction of components D and B. We can write our mole fractions in terms of the two epsilon values of the reactions. However, that will still leave us with three unknowns, and the added complexity in terms of the analytical expressions when we write them in terms of epsilon 1 and epsilon 2 will have no benefit. Easy way to obtain a solution is to make pressure the subject of the equation in each of the equilibrium expressions, realizing that pressure must have the same numerical value, and from that we can solve our equilibrium mole fractions. Back substituting into either one of the equilibrium equations will result in the pressure, which is the answer to our question. In terms of selectivity, enthalpy of reaction values show that both the reactions are endothermic. With a decrease in temperature, a decrease in the equilibrium constant is expected for both the reactions. According to Van 't Hoff's law, the slope of this dependence on temperature of ln of the equilibrium constant is a function of the heat of reaction. Since reaction 1 has a much lower heat of reaction than reaction 2, the effect of a decrease in temperature will be much more significant on the equilibrium constant for reaction 2 than that for reaction 1. Subsequently, the selectivity of reaction 1 in terms of reaction 2, if equilibrium is concerned, will increase with a decrease in temperature.